welcome back to the fundamental theorem. So, continuing with our series on logic, I just want to take a moment to briefly discuss sets and logic. Now, the reason why I wanted to talk about sets specifically, the reason why I in fact choose to dedicate an entire video exclusively to this subject is because this is how you're going to encounter logic uh, most commonly at, say, the high school level. And the reason why I want to talk about sets and logic is because, well, it is a useful way to visualize what it means for there to exist some condition or for there to exist a combination of conditions using the operators that we discussed in the previous video, that is, and, or, and not. Now, I will, of course, make sure that this remains entirely like a detour or a side note from the main subject, which remains Boolean algebra and propositional logic and stuff like that. So, without further ado, let's dive right into it. So, before I go on ahead, I just want to take a moment to recap. What exactly is a set? Well, as you should know, a set is essentially just a collection of stuff, right? So it could be something like the set A, as you see on your screen, which is, well, it just consists of the elements 1, 4, 9, and 16. In this case, the elements of the set are numbers. Now, what if I said, I don't know, all the people in your class? Well, those aren't exactly numbers, but that's still a set, right? A set need not be finite. It need not have only maybe 4 or 5 elements. It could have infinitely many elements, right? If I talk about, say, the set of all prime numbers, now that's infinitely big. It contains infinitely many elements, but it's still a set, right? So you could take pretty much anything you like. You could take the furniture in your room. You could take the names of your best friends, and essentially you could just club them together into a set, and that would be perfectly valid, even mathematically speaking. Now, when dealing with sets, there are certain useful notations that we use just to expedite the process of, actually referring to stuff that we do with the set so that we don't have to say it in so many words, right? So let's look at probably the most common symbol, which looks a little bit like either an E or maybe even the Greek letter epsilon, if thought of from a certain point of view, I guess, or like the euro symbol, but without two dashes and with just one. Either way, however you like to think about this symbol means element of, or in, or belongs to, and it's known by all of these different words, but all it really means is, well, if I say some number in A, all I'm trying to say is, well, is that number actually found inside of A? So in this case, I've taken the liberty of actually defining it specific to A. So if I say some number in A, that means that number is either valued as 1, or it's valued as 4, or it's valued as 9, or it's valued as 16, right? And there's actually a very specific reason why I chose the OR operator here. And the reason why I did that is because it is sufficient for that number to be any of the numbers 1, 4, 9, 16 in order for the statement some number in A to be true, right? So essentially what some number in A does is it checks if that number is inside of A, and if so, it would be valued at true, and if not, it would be valued at false, right? Now, let's say that the number in A could actually possibly have two values. Maybe it could either be valued at 1 or it could be valued at 9. And well, the statement some number in A would still be considered true because it doesn't matter whether it's 1 or whether it's 9, it's still going to be in A. So you see, that's pretty much how the in operator works. Now, I'm only going to consider the in operator. There's other operators as well, such as subset, subset of equal to, and all of these different things. But well, for the purposes of this video, I think I'm going to focus only on in because there's a lot more meat that we need to dive into. Okay, so just without further ado, let's look at another quick example. You see you see the set B consists of the numbers 0.1, 100, and 4.1957. There's no reason why I chose those numbers. They're completely arbitrary. And well, let me ask you, is 5 in B? What would be the truth value of the statement? Well, clearly the number 5 is not present in B. Therefore, the truth value of this statement is false, or 0 as you would express it in binary. Now, like I said, this is just another quick example. You could say that maybe I have a class of 4 students and they're called John, Henry, Mark, and Thomas. And then I ask you, is James in the class? Well, does James belong to this set? And clearly, the word James is not present, which means that the truth value of the statement, James in class, is yet again false. Now, there are certain important sets that you need to be aware of. And again, I'm just doing this because this is just general knowledge, to be frank. This has absolutely nothing to do with sets and logic. I just want to pop this in here so that you can have a look. And yeah, it's just useful stuff to know. And now, the real crux of sets and logic has to do with the why. And as you know, what I really stand for with this channel is getting to know why, right? Well, the reason is pretty simple. A set usually consists of elements that share some kind of relationship. And I know I chose completely arbitrary numbers like zero point 0.1 and 100 and 4 point, I don't even remember what the decimals were. But, well, those numbers too have something in common. And what they have in common is that I chose them arbitrarily, you see. So no matter what sort of set I have, no matter how I choose to group different elements, they will pretty much all of the time have something or the other that puts them together in that set, right? And that's where this whole idea of logic and conditions really comes in. You see, the way you actually write or represent the set of all numbers that satisfy, or set of all elements that satisfy a certain condition, is using this notation. I mean, first of all, as you probably figured out by now, sets are usually represented inside curly brackets. And over here you have the notation curly brackets elements, and then you put a colon. Some people also use a vertical, the bar, yeah. And then you talk about what condition under what circumstances you wish to choose these elements. So in this case, you can see the set of all squares of natural numbers. So essentially that's 1 squared, 2 squared, 3 squared, 4 squared, and so on. And if you notice 1, 4, 9, and 16, that is the first 4 digits of the set, are actually what I chose for A. And that's just a little bit on the side. But you know, the best way to sort of condense this is by saying set of all x squared, where x is in n. And n, as you recall, is the set of all natural numbers. Now, if you, the real reason why you would want to represent sets in this sort of condensed fashion using these conditions is because, well, when you think about it, the set of all natural numbers is infinitely big, right? Do the numbers ever end? Of course not, right? That's what the word infinity literally means, not ending. Well, the set of all squares of natural numbers is obviously also going to be infinitely large. But you see, I don't need to have any of this sort of ambiguity that I do with like 3 dots or something like that when I represent it in the form set of all x squared, where x is a natural number. You see, that sort of removes all sort of ambiguity from the earlier representations, which all consist of 3 dots. And the reason why this is useful is because in mathematics, we want absolute unambiguity. You know, if I say something, we can't afford for the same thing to be interpreted 100 different ways. You simply can't afford to do that, because thing is, with math is pretty much as close to something absolute as we have ever got, right? And logic is what makes it so. Logic is the backbone of the sort of accuracy as well as the precision of mathematics and mathematical language. And that's why it's useful to condense things into these sort of notations where we can take best advantage of unambiguity. Anyway, now let's get back to logic, right? So let's say I have 2 conditions A and B. All right. So what I can actually do is, well, I can draw what's known as a Venn diagram. And what a Venn diagram means is, well, essentially each circle, right, in this case A and B, represents the set of all elements inside the gigantic box that satisfy condition A, right? So that's the yellow circle, and the green circle is the set of all elements in the gigantic box that satisfy condition B. So, the reason why you would visualize sets using these sorts of diagrams is because you can have certain relationships between sets. Like over here, I just have two sets, but over here, as you can see, there is a certain portion that actually overlaps. And well, that's definitely possible in real life circumstances, right? Let's say you want an SUV. Let's say A is the set of all SUVs and B is the set of all blue motor vehicles, right? So these two sets are clearly not independent of each other. It is definitely possible to have a blue SUV, which should fall right in this little overlapping area between the two sets A and B. So, as you can see, given that the conditions A and B are essentially the definitions of the sets that you can see represented by the yellow and green circles, respectively, Venn diagrams that are used to represent sets can also be used to understand the relationship between elements satisfy certain conditions. That's pretty useful. So anyway, as you can see, this sort of overlapping area, well, this corresponds to the condition A and B. So when you actually think about it, all you need for that to be a set is a certain group of stuff, right? And that stuff is pretty much always related. So in this case, the quote unquote stuff represented by the area shaded in gray is, well, the elements that satisfy condition A and that also satisfy condition B. In other words, this is a set of all elements that satisfy the condition A and B. And in fact, geometrically speaking, this area would be called an intersection, and that makes perfect sense because it's where a quote unquote, I mean the yellow circle quote unquote intersects or has common area with a set of all elements B, right? And the way this is represented mathematically or using set notation is you see A and then you see this sort of, it's like an upside down letter U, right? And then you see B. So essentially, this means set A intersection B. What that means is the set of all elements that satisfy, both condition A and condition B. Now, there are other things that you could actually do with this diagram. What if I shade the entire thing, like everything that's inside the circles? Well, think about what that actually means. If you like, do go ahead and pause the video. Think about it. What this means is you have SUVs, and you also have blue cars or blue motor vehicles, and you club both of these together. So an element would be in this set. If it's in set A, it would also be in this set if it's in set B, right? In other words, it would be in this set if it satisfies the condition A or B. It is sufficient for an element to satisfy one of the conditions A and B in order to be in this set. At the same time, it is also possible for an element to satisfy both conditions A and B. So you can see A and B or A intersection B is actually included inside this shaded area. And for those of you who are familiar with uh, more advanced stuff regarding sets, that would mean that A intersection B is a subset of A union B. Oops, I gave it away. Well, this region is called a union, and for obvious reasons, essentially what you're doing is you're just taking two things, you're putting them together, boom, so union. And this is represented using the letter U. Now, let's say we just have one set, right? And well, based on the fact that we've examined and or, it's pretty obvious that we're going to examine not right now, right? But what would that look like? Well, geometrically, essentially, it would be all elements that are inside the big box, which incidentally is known as your universal set, right? As in the set from which you're considering your elements. Because, I mean, when you actually think about it, you can't actually be talking about every single thing in the world, right? In the universe, in all universes. Well, no, you need some sort of restriction, and that's what the universal set stands for. Now, set of all elements not in A essentially means a set of all elements that do not satisfy the condition A. And that's just going to be everything that's still inside the universal set, of course, but that's outside of A. So you just shade everything outside of A. And well, this is obviously not A, as we said. And this is what you would call the complement of A, right? And don't confuse this with the word COMPLIMENT, because that compliment is when you meet someone and you say something nice about them, like you look great or something like that. That's a compliment with an I, right? This is a slightly different idea. Well, the reason why we would call it a complement is something that we can actually get into a little later on. All it means is if two things are complementary, it means they pretty much add up to one certain thing, right? And we'll get to that in a bit. We'll get to what this means. So, what I want to take a moment to look at is the number of elements, right? And the number of elements in a set is usually denoted by small n, and within brackets, you put the name of that set, right? So, let's just take a look at, for example, n of A or B. Now, remember how in pretty much when you were in elementary school or something, you must have been taught when you put things together, you add, right? Yeah. And well, it's very tempting to say n of A or B is just going to be n of A plus n of B. And well, that's not always wrong, right? But it isn't always right either. And the reason for that is, well, if you take n of A, if you take n of B, that's not all that's present in this picture. There's also a tiny little region in the middle that is n of A and B. And if you really just take n of A and you take n of B and you add them together, you see this region n of A and B, you're kind of adding that region two times. So essentially, n of A plus n of B is essentially going to contain the region n of A and B two times. In other words, it's going to be n of A and not both A and B, right? Plus n of B and not both A and B, right? And two copies of n of A and B. So the way we fix that is just subtract one of those two copies. And hey presto, we have n of A plus n of B plus n of minus n of A and B is equal to n of A or B. And this is a pretty useful thing to know. I mean, it's elementary, it's elementary stuff, but you really should know this. Okay, now let's consider n of not A, right? And well, it's actually fairly easy to understand what n of not A might look like. And well, you can actually just think about this in terms of any old everyday example. Let's say I have five pencils, and let's say one of them, and only one of them, is red in color. So if I asked you how many pencils are not red in color, well, the answer is pretty obvious. You would say four, right? And well, how did you arrive at the number four? Well, you said, okay, there are five pencils, and only one of them satisfies the condition that we do not want it to satisfy. So essentially, we just get rid of it. And that's pretty much all you have to do here as well. N of not A is simply going to be N of total, that is the number of elements in your universal set, minus n of a. And this actually makes even more sense when you kind of sort of rearrange it a little bit. You actually get this n of not a plus n of a equals n of total. And that's what I said earlier, right? If you say that two things are complementary, it means that they sort of add up and give you like this one certain thing. And this is where that actually comes from, because if you add an element, and I mean, if you add the set of all elements, if you add the number of elements that satisfy a given condition and the number of elements that do not satisfy a given condition, well, what are you left with? The number of elements, right? And this makes perfect sense. Now, all right, I want to take a moment and look at what's known as probability. Now, probability essentially refers to likelihood. It is a measure of chance, if you will. And what it means is, well, you want to know how likely it is that a certain event or that something that you want, right, a certain condition will be satisfied, right? And well, obviously, probability is never going to be exact. You see, if you toss a coin, there's a 50% probability that it's going to land heads and 50% that it's going to land tails. Now, that doesn't mean that after it has landed, it is half heads and half tails. Like, no, it either lands heads or it lands tails. So, probability of an event happening does not necessarily guarantee its outcome, but rather it suggests how likely it is that that specific outcome will be realized. Yeah. And the way you can actually measure this is by using simple ratios. The ratio of the number of elements that satisfy your condition uh, to the number of elements in total, right? And if you go ahead to your heads and tails scenario, for example, there are only two possible outcomes, right? It can either be heads or it can be tails. Now, let's say you want to find probability that it lands heads. Well, there's only one way in which it can possibly land heads, right? There's only one configuration of the coin at heads, right? So that's one. And in your denominator, like I said, you have only two possible configurations, so it's two. So that means the probability that it lands heads is 1 in 2, or 50%, as I said at the beginning, right? Well, what this means is when you have number of elements satisfying a condition, if you just divide the whole thing, like just take everything you have divided by n total, you're pretty much going to end up with a probability of some sort. So why don't we just go ahead and do that? So if we do that, we find these two identities. Probability A union B is equal to probability A plus probability B minus probability A intersection B, and probability not A or A complement plus probability A is equal to 1. And well, that pretty much wraps up this quick discussion of sets and logic. And the reason why I wanted to talk to you about sets and logic is because very often when you're dealing with situations either in real life or even theoretical stuff, you might be confronted with a case where you have relationships between sets. And if you want to find, if you want to sort of numerically describe these relationships in terms of either probability or number of elements or stuff like that, you can reliably use these ideas to figure out what it is you want to figure out, right? And I just want to leave you guys with a quick puzzle that deals with Venn diagrams. So I've put the source over there as well, right? Um, they haven't actually listed down the elements there. Again, this entire setup deals only with the number of elements. And as you can see, the letter U actually refers to universal set. So essentially that big box that you see over there, right? And well, this puzzle should test your understanding of the logic that we have covered so far and what logic can mean geometrically when dealing with conditions represented as sets in Venn diagrams. So, well, that was a mouthful and a half. And yeah, that's pretty much it for this video. Thank you guys so much for watching. Please, please do like, comment, share, and definitely hit that big red subscribe button down below. And do check out some of my other videos on logic as well as on trigonometry. I've made a series trying to simplify trig and make it a little more intuitive to understand. And I'm actually running the trig series and this logic series kind of parallelly. So I don't know if my next video is going to continue the logic series or if it's going to instead be about trig. But whichever it is, I do hope that you stay tuned and check it out when I do release it. So thank you guys so much for watching. See you next time. This is the Fundamental Theorem signing off.